conclusion that was reached.
Does it dominate the action in any way? Because you said experimentally the moment you have polarization, boom, or maybe the dipole is not large enough, or
I don't think so, but that's a great question. We should look at that. Look, I mean, there's a lot of extra details that we're taking into account in the calculations that I'm not 100% on top of because I didn't do them myself, but I'm sure Mary B would have a good answer. And there's a long supplement to our paper. But
Yeah, we have time for one more question.
I'm fine.
you think this you hold can you access activity?
Yeah, so if you would, and I think that was kind of our original thought process, that we could make some sort of structure where you could add polarization in, and then you could really write it on the scale that you want. So for example, if you could engineer some domain structure on the scale, scales of tens of nanometers, you might end up with something very efficient, because if that's the length scale that you need, right? And one way to achieve that is through processing, but another might be through manipulation of ferroelectric. That was actually kind of where we thought that we would go with this project. We never quite got it there, but that's definitely a good idea and kind of where we thought we'd go with that. Yeah.
Okay, let's thank our speaker, Master Green. The next presentation will be given by Alex Demkov, Steve goes to University of Spain. We'll be done with
It's 2 different bikes.
And is that one working?
Not obviously. I think that was more for recording. I know it's
Yeah, that one just shut off during your answers.
it did. Hello. That thing's dead.
Maybe we have to back up.
Hello. This one I'm sure.
Yeah, so that one's just for the computer. So go ahead and take that. Maybe a little down.
Right. Hey, can you hear me? No? Maybe a little bit up. Okay, good. Thank you so much. I would like to thank the organizers for giving me this chance, but I realized last night looking at the talk that I really wanted to come here, so I promised to talk about everything in just 20 minutes. So I'll have to go really fast. The work actually is done not by me, but by the graduate students. So this is Venti Lee, this is Tess, this is Mark. Mark is down there. And then this is Inwan, and this is Agam Posadas, who is a staff scientist in the lab. And I'll talk about the electro-optical response of barium titanate thin films integrated on silicon, actually. So this is the plan. First, I'll tell you about electro-optical effect and sort of why you want to do something like this. And then there are 3 topics I'd like to cover in the next 15 minutes. One is the effect of domain morphology, sort of microstructure, on the electro-optical response. And then the second one is what gives you a particular microstructure. That's actually thermal history of the sample, because we grow them with high temperature processes. And then in the very end, I will talk about the microscopic origin of the electro-optical effect in barium titanate. Let's see. So what's electro-optical effect? There are 2 actually. One is German, one is Scottish. And so I'm interested in the German one because that's it's good for ferroelectrics are good for that. You have to be non-center symmetric to have a linear electro-optical response, right? The Kerr effect is also kind of like weak, so we'll concentrate on the Pockels effect. In a nutshell, it's a very simple thing. You apply electric field, your refractive index changes, right? And so why does it change? So here it's written in terms of the dielectric tensor, but it's the same thing as refractive index. The idea is if you apply electric field to a material, first of all, you tilt the bend structure. So all of your transitions are now changed, and that's your Chi2, right? Chi1 doesn't depend on field, but Chi2 does. Nonlinear susceptibility, high frequency response, electron response, so it's a high frequency. But you also grab your ions, and we know that susceptibility normally is computed for the equilibrium position of ions. If you apply force by electric field, they are shifted, so you can expand in Taylor series. This is the first derivative of chi, and so that's called Raman susceptibility. That's a Raman effect. And this is optical phonons. But in materials like barium titanate or lithium niobate, they're piezoelectric. And so if you apply electric field, you have converse piezoelectricity. It changes the lattice constant. That changes the band structure. That changes Chi1, right? And so they're actually different frequency regimes. At low frequency, all of them play out. At high frequency, only electronic Chi2 works. In intermediate, you have both kinds of phonons, and so you can see how the effect changes. Let's see. Okay, if you look at all the materials under the sun, which have been measured for the electro-optical activity with a linear electro-optical effect, the material everybody is using is lithium niobate, but actually has a very sort of modest electro-optical response, only 35 picometers per volt. Now, one thing I have to tell you, these are all very weak effects. You measure in picometers, so it's really tiny. Now, barium titanate, on the other hand, is a great material because it has 1,300 picometers per volt. And there's very few, potassium titanium nitrate, niobate is slightly better, but in principle, this is one of the best materials you can work with. So that's what we're going to focus on. Come on, do something. Okay, all right. So what are you going to do? First, you need to take barium titanate, and you need to confine light somehow. There are various ways of doing that. You can etch a ridge, or you can put something on top which has a dielectric constant difference. And so you're trying to make the light going along this green line. You make a waveguide. And then you put contacts on top, and you apply electric field. In this case, it will be parallel to the surface. So this only works for TE mode. So that's a specific kind of design for the waveguide. And what you do, you change the speed of light in this path. So you can get a phase shift, right? And so the phase shift actually is directly proportional to this R, which is the thing which changes the refractive index. That's your Pockels coefficient. It's really an ugly tensor, but let's say there's an effective number which just says that if you apply a certain field, there's a delta N caused by. And so it goes right there. And so the figure of merit for such a device is so-called V pi L. It says how much voltage for a given length you need to apply to change the phase to pi. And so if you make two paths like this, and you shift one by pi, you'll get no light at all. And so now you have a modulator. You can go like Morse, 0, 1, 0, 1, And so materials like lithium niobate and barium titanate have been tried and they work. And so this is, for example, a racetrack modulator, and this is called Max-Zander. Doesn't want to follow me. Okay. If you build a device like this, you can make a lot of interesting things. For example, this is so-called LiDAR on a chip, right? What you do here, it's a beam steering. You send light in through the waveguides, and then you judiciously choose the phase shifts, and then you recombine them, and it allows you to steer. Now, that can be used in a car which drives itself, and so it can avoid your favorite dog. You also can make the chip-to-chip communications. Barium titanate works really well at 1.55 microns, so it can talk to fiber directly. Okay, so this is why I want to do this. I want to build an electro-optical modulator, except for my material doesn't look nearly as pretty as I wish it would, right? So it kind of looks okay on this scale. This is 0.2 microns, so it's a nice barium titanate on silicon. And I want to do all that within silicon photonics because they have a manufacturing infrastructure, right? Now, if you zoom in, this is now 15 nanometers. Our dislocation looks kind of ugly. And then if you go zoom in even more, now it looks perfect. But we know that there is something wrong with the system because it's not uniform BaTiO I'm finding in the textbook, right? And so for that, I need to understand the microstructure. Actually, I can do microscopy with geometric phase analysis, and I can look at the strain maps, and I see that my film is actually C-oriented, meaning polarization is out of plane due to compressive strain. I use STO buffer to put it on silicon. But as I go thicker, I get this sort of A domain, meaning polarization now is in plane, which is what you want for TE modes. right? Because my light goes this way, polarization is that way, so ferroelectric should be the same direction. But you can see it's a complicated thing, and I want to understand how that controls the electro-optical response. But I cannot do first principle calculations because it's just too big, right? So what we do, we use LQ Chen's phase field Hamiltonian. We use a particular implementation of that with the finite element code developed by my colleague Chad Landis and his students. And it allows you to actually simulate fairly large chunk of the material. And you can, it's you know, there's a cube and there's polarization, dielectric tensor, everything is stored there on a mesoscopic scale. And so it allows you to model something like this, and you can see what, you know, what polarization is doing, what your dielectric tensor is doing. And so it sort of shows me that under these strain conditions, indeed, at the bottom, I'll have like C-oriented domains, and then there's transition region. If I go up, you know, some of them going this way, others are going that way, which means that if you look on the film from above, it looks like that. There's two domains. These are crystallographic domains. Inside each of them, you're also going to have ferroelectric domains. So it's a mess. And so the question is, can you figure out what it is? And so we go through the whole simulation cell. We average out the values. We get the strain. And then we figure out what the lattice constant is. And we assign the phase. The Hamiltonian actually is fitted to reproduce the barium titanate phase diagram. It's not fitted to produce electro-optical response, right? So, but that's what we're actually interested in. And so you can do it two ways. Because I have the full expression, I can actually take a derivative of the dielectric tensor and analytically calculate what the Pockels coefficient at every node is. And so this is what I'm showing here. But I also can just apply the field and measure it, so to speak, computationally. And so what I do, I look at the various components of the dielectric tensor at various values of the field, which is normalized to some fixed value. And I take the slope, and that is the Pockels component of the tensor. The good news, qualitatively, it works. The bad news, the one I'm really interested in, which is R42, is way, way underestimated. It's supposed to be 1,000. It's coming to like 140. But qualitatively, we can do that. The most important message from this study we did was that if you start with different microstructure, your Pockels tensor changes locally. And so you need to know what kind of a field you have to predict the electro-optical response. And that brings us to the next thing is, you know, we start growing at 750 C. At that temperature, barium titanate is cubic. It has a huge thermal expansion coefficient, 10 times bigger than that of silicon, right? And it sits on silicon. And so now I'm coming down in temperature, going to room temperature. I have no idea what this thing does. I don't have any in situ measurement, right? And then I have to make a guess. And essentially what we did, so this is, you know, the famous diagram, right? Where they show the whole phase diagram of barium titanate as a function of temperature and strain. So negative here is compressive, and this is tensile. And so here you see it's orthorhombic of various kinds. There's monoclinic phase, here's tetragonal, here's, you know, and so how do you know where you are? Well, you don't. And so we make guesses. So essentially we said there are two limiting cases. One is you're fully strained, and the other one is you're fully relaxed at high temperature. And then, you know, you have to, you know what each lattice constant is doing, so you can actually then go and run the simulation and follow a particular scenario. And it turns out that if you're fully strained, you maintain sort of the tetragonal phase all the way through. At any temperature, it's all tetragonal BaTiO. However, if you're fully relaxed, you actually can end up into what you would call AMM2, right? It's an orthorhombic type thing, right? So your polarization actually isn't a plane, but it's a different phase, right? And so we think we're somewhere in the middle. And so you have the sort of the top of it has an in-plane polarization, and the bottom is the tetragonal. And so, but the good thing is, we know that from the previous thing, we know that microstructure determines the local variation of the electro-optical tensor. And then we know that the thermal path will determine what you get. And actually, you know, before I looked into electro-optics, there was always this controversy. Your barium titanate grown on silicon. Is it in the compressive state or in the tensile? And there are reports which are both. And I think it's because people cool at different rate. Essentially, if you want to follow this one or that one, it depends how fast you cool. Right? And so I think different people cool at different speeds. It depends, you know, if you have, we have very thick things, we have to cool slow, otherwise they crack. But if you have a very thin film, you can cool really fast, like 30 degrees per minute. And the microstructure will be different. And then it will give you a different electro-optical response. All right. So now we're going back to saying what actually is this electro-optical response. So this is the formula I already showed you. If you look at the ionic phonon response, it sort of looks like that. So this is the derivative of chi1 with respect to atomic displacement. So that's the Raman effect. This is the Born effective charge. This is the frequency of the mode. And so if you want to do first principle calculations, your best bet is rhombohedral phase because it's dynamically stable. And here, everything you can actually understand, everything works. First principle theory works perfectly for what you're not interested in. You know, it's like in Little Prince. If you have hunters, you don't have chickens. If you have chickens, you always have hunters. And so, so what I'm plotting here is, so that these are the dipole moment of the mode polarizabilities. This is the Raman response. These are the displacement in each mode at the gamma point placed by atom. And these are the atomic displacements in the modes, which gives you a large Raman response. So in essence, in this system, we're kind of lucky. There are 3 modes down here with reasonably high Raman susceptibility. What it means, you move atoms and chi1 changes. And the reason they do it is because you move titanium with respect to oxygen. And so let me skip it quickly. So essentially, you're changing the hybridization. So you can see that in the inactive Raman mode, you move the atoms, nothing. I'm checking the band gap because it's the smallest transition. In the Raman active mode, your band gap changes quite a bit because it's titanium oxygen splitting. So we think we understand that we got the numbers, it's all working, but I want to know tetragonal phase. And that's a real problem. So if you try to do the P4MM, nothing works. Not only is dynamically unstable, but nothing works, right? And so we're looking in the literature, arguing with the reviewers, came to a conclusion that, well, there's Michelle, that the reasonable structure you need to deal with is actually CM, where you displace atom along 1, 1, 1. And then you take like 8 of them, and you can always make it into P4MM. If you do that, then everything works more or less well, except for, actually, oh yeah, and this is Trinity, I'll skip that. And I'll skip that. So everything works, and you get the active and inactive mode. And the only problem is, so this is the ionic response. So this is 820, this is just ion. So that's what you call the clamped one. And then we can calculate the unclamped one by looking at the piezo response. All of this works more or less well. So we get the right numbers. The only problem is you can't cheat nature, right? This is a highly anharmonic system. So I'm looking at the potential surface, which has nothing to do with the real thing. You need to look at the free energy surface. There are 2 ways of going about it. You can try to recreate it by adding the phonon entropy, doing quasi-harmonic approximation, or you can do MD, right? You can add energy to your system, run MD, and see what the entropic contribution is. Then you'll be anharmonic. It's very expensive. So now I think we have a reasonably good thing. We know it's not quite right. Now you ask, does it all work? So this is just to tell you that it does work. So we built, well, not we, Goran Mashanovic at Southampton built the device. They're all working. We get fairly respectable VPIL, and there's some modulation. So here I will stop, and I'll leave the conclusions. You can read them, and I will be happy to take questions. Thank you very much.
For interesting talk, we have time for questions.
From Luxembourg. Yeah, one question about the statement that you have this contribution in your extension that states with the optical phonons and the Raman response. In barium titanate, the Raman spectrum is also dominated by mode coupled